Welcome everybody to this new edition of the DinAmicI Internet Seminar. Today's speaker is Andreas Knauf, Professor of Mathematical Physics at the Department of Mathematics of the University of Erlangen, and is going to talk about asymptotic velocity for scattering particle. Before starting the seminar and giving the word to Andreas, just a few words. There is live streaming on YouTube. So if you unmute yourself to ask a question or show your face, you are implicitly accepting to be live streamed on YouTube as well. But if you don't want, you can always use the chat. If you ask a question on the chat, I will look at it during the talk and I will ask the questions for you. So feel free to choose either way. And so without further ado, please, Andreas, thank you for accepting to give the seminar.
Okay, so thanks a lot, you organizers, and I'm very pleased to be in Italy again, only virtually at this moment. And okay, this will be about a subject in mathematical physics, so particles scattering. And so this is a long ongoing work, and there have been publications with Jacques Fejoz and Montgomery. There's a nearly finished publication I won't talk about at the moment with those two, just proofreading, and there's an unfinished one that will be related also to the subject. Then there has been a doctoral thesis by Stefan Fleischer with me, with two articles being published, and there's an ongoing doctoral thesis by Manuel Quaschner, who is attending this meeting, and so this will be partly about joint work and work of these people. Okay, so just for a short overview, we are considering n-body problems in rather general sense. Still, it would be a good idea to think of the classical n-body problem of n mass points acting by gravitational forces and interacting in space. And then, especially in this case, one would think that certain phenomena may happen, but they are improbable in the measure theoretical sense. Let's say having Lebesgue measure 0 or Liouville measure 0. I will be more specific. So one of these will be collisions of particles, then a more subtle thing, non-collision singularities, and the last point already being announced in the title, non-asymptotic, non-existence of asymptotic velocity. So typically asymptotic velocity, that is a Cesàro limit of velocity, should exist. Okay, so accordingly, I will touch upon these three questions and also talk about some methods that are related to work on these questions. And in part one, there's a rather general method based on technique of Poincaré sections that enables us to show that certain sets in phase space have measure 0. And this in part two will then be applied to this problem of collisions. It will also be applied to the other problems, but there will be additional ideas coming into the problem of non-collision singularities and non-existence of asymptotic velocity. And this will be modeled by looking at non-deterministic billiards. This will comprise part 3 of my talk. And so in part 4, all these techniques will then be applied to non-collision singularities and question of asymptotic velocity. Okay, so I have just start with this question of this Poincaré section technique, and the setting will be rather general. So we have a smooth manifold with a volume form omega and some vector field x. Of course, this vector field then generates a flow on this manifold. But in the applications, this manifold will typically be non-compact. And yeah, of course, there is some relation between the volume form and the vector field, namely the Lie derivative of the vector volume form vanishes, which means that volume is being preserved. So maybe think of Hamiltonian dynamical systems or something like that. Yeah. Okay. So now by just general ODE nonsense, we have a unique solution of this initial value problem for this differential equation and call this phi. So if the vector field is C1, then this phi is C1, and then there's a maximal domain of definition for this phi. So you have initial data x, time t, and phi of t and x gives you position at time t starting at x, like normal. And this is then a subset of extended phase space. And it can be, for a given x, the time interval can be written as an open time interval between escape times t plus and t minus. This is just ordinary, it's just introducing notation, in fact. And because typically everything will be sufficient to consider positive escape times, I just denote them by t. Yeah. Okay, so the D is an open set, and that's what it is. Yeah? Now, we look at points in phase space that are wandering, and you see, because we have these phenomena like collision or non-collision singularities or so, we have to cope in our definitions with the possibility that really time to collision or this escape time is finite. Yeah, so also we somewhat adapt a known notion of wandering set to this situation. So for us, the wandering set for this maximal flow phi consists of those phase space points x that have some, let's say, open neighborhood ux and some minimal time tx, so that if you intersect ux with a time transported ux, namely for times larger than this minimal time tx, then you get empty set. Yeah. Okay, this is for dynamicists. This is just quite usual kind of definition. Let's say for the free flow on R2, where velocity is kept invariant and position is just modified by at time t as position at time 0 plus velocity times t. The wandering set is everything in phase space except those where velocity is 0. Yeah? So you have ux, then you have this set of the time transported ux for minimal time 1/2. So this looks like front of an ICE train, I would say. And so this is empty intersection. Yeah? Okay, that's the wandering set. And that's what we are somewhat interested in. And why are we interested in, for example, if we define the singular set to be just a set of phase space points where the escape time is finite, then this singular set is part of the wandering set. Yeah, so of course the singular set is Borel measurable because this escape time is lower semi-continuous, and you may have a flow box argument showing that the singular set is wandering in the sense defined before. Okay, so now we would like to show that the singular set for dynamics that are of interest is of measure 0. So, of course, this wandering set may be very big, yeah, not of measure 0. So we have to have a second concept, not only the concept of this wandering set, but also these concepts that are the concept that is connected with these Poincaré sections. So our phase space was called P, capital P, and then we have a sequence of Poincaré sections in P, yeah, called HM. And just to be a bit pedantic, I say that these are codimension 1 closed submanifolds with boundary, yeah, and okay, call them Poincaré surfaces. And boundary, this is, I mean, just this bar refers to the boundary. Now, what are the assumptions? The assumptions are first that this vector field that generates our flow is transversal to the relative interior HM of these Poincaré sections. So this is just the embedding. And now with the inner product, the I being just the fat I here, because this vector field is transversal to these HMs, we can take the differential form of codimension 1 on P, call it nu, and then restrict this differential form to these Poincaré sections, so their relative interior. Yeah? And then, because of this transversality, this gives us volume forms on this codimension 1 surfaces. Yeah? And of course, this is very clear. The second assumption is now that these volumes are in fact finite. This volume of this sequence of Poincaré sections, and goes to 0 as the index of these Poincaré sections goes to infinity, this n. Yeah? So there's Poincaré sections of smaller and smaller volume in phase space. Now, the second concept here is the concept of transition points. That's again,
Andreas?
Yeah.
Sorry, there is a question.
Yeah.
Do this have codimension 1 in the manifold or in the tangent bundle?
No. These are just think of P really as a phase space. Yeah, and so the codimension. So first of all, these Poincaré surfaces are of codimension 1 in phase space. Yeah, whatever phase space is in the concrete application. Yeah, and then because this omega was a volume form on P, the Ix omega is a differential form of degree 1 less than the dimension of P. So it has a chance to be restricted to a volume form on HM.
Thanks.
Okay, you're welcome. Now, okay, a point X in phase space may or may not be a transition point. Huh? And the set of transition points is the set of points whose forward orbit hits almost all of these Poincaré sections. So that means all beginning from a minimal index M0. Yeah? So this is a second set, which is also measurable by just abstract nonsense. Yeah? So we have this set of wandering points, we have this set of transition points, and now the first statement comes. If you combine these, so if you intersect these two subsets of phase space P, then the volume of this subset is 0. Yeah, so that's a general technique that we want to apply to show that certain sets in phase space are of volume 0. Of course, the technique can only be applied if the subset of interest is in both sets, it's wandering and it's composed of transition points. And of course, this depends very much on the concrete definition of Poincaré sections or this family of Poincaré sections that one uses. Yeah. Okay, so this general result was published last year, Stefan Fleischer. Okay, so just to see the point of this theorem, just a short remark. You have an intersection of two parts in phase space, wandering set and set of transition points, and both are typically of positive measure. Yeah. So, for example, in this free flow example, almost everything in phase space R2 was wandering. So the natural Lebesgue measure in this case of just volume of R2, except this part of non-wandering set was infinity. Yeah, so this is non-zero clearly. Also, if you have an ergodic flow on a compact manifold P, no matter how you choose your Poincaré sections, almost everything is transitional in this sense. Yeah, so it's a combination of both sets that makes the measure zero result. Okay, so just to give you a gist of how to apply this in concrete situations, just a little example for mechanics. So you have one particle in this examples, and this example, it has the classical Hamiltonian kinetic plus potential, and this potential is assumed to diverge at position 0 in RD, and also at infinity, this potential may diverge, but not too fast. So maybe be bounded at infinity or just grow at infinity like q squared, just to make sure that the particle cannot go to infinity in finite time. So the second assumption is not very important. The first assumption is very important, namely that the potential itself may diverge, but only with distance from the origin to the power minus alpha, and alpha being smaller than 2. Yeah. Okay. Need not be homogeneous, can be just estimated from above in absolute value by this power law. Okay, then how can we apply the method? So what we first notice is that if an initial point x naught is singular, then this means that really the position goes to 0. This is the only way to be singular in this case. Yeah? Just to be caught in the hole at the origin. Yeah? Very simple situation. And now we want to show that these singular points make up a set of volume 0. Okay, how can we do this? So of course, we would like to have this kind of statement not only globally in phase space, but for every energy surface, sigma E, by which I just denote h to the minus 1 of E. So these are hypersurfaces, and okay, in the regular case, I mean, we have this Liouville measure on these hypersurfaces. In the regular case, this is just a submanifold. And now the question is how to define these Poincaré surfaces HM. So HM should be of codimension 1 in the energy surfaces. So in phase space, these HM at the moment are of codimension 2. And one way to define this is just to let these Poincaré sections project to spheres in configuration space of radius 1 over m. Yeah, so here is configuration space. Here you have your singularity. The Fm are of radius 1 over m, just these spheres. And to make a Poincaré section out of this, you just look at corresponding momenta, so that Qp is in the energy surface, and that the scalar product between momentum and position is negative, so that you're going inwards. Yeah, and then you have this family indexed by m of these Poincaré sections, and everything that is singular, everything that collides with the origin in configuration space, must be transitional at this energy E. Yeah, must intersect almost all of these Poincaré sections, because at the beginning it has a positive distance to the origin, so there are infinitely many of these Poincaré sections inside and only finitely many outside. Yeah? And on the other hand, because of compactness, it is also clear that these Poincaré sections are of finite volume, all of them. And also it is clear that these HM with a strict inequality, strictly moving inward particle, are really transversal to the flow. Yeah. So in this sense, we just have to have a general argument that going through the boundary of these Poincaré sections give you measure 0, and then you are basically done by, if you can show that this volume goes to 0 as m goes to infinity. Now, the phase space volume of these Poincaré sections inside the energy, energy surface E. Okay, now that's a very concrete analytic problem, and now it's simple to solve this. And just one remark before solving this, just thinking about the problem, it is clear that the configuration space must be at least two-dimensional, because if you have one-dimensional configuration space, then it's clear that almost everything can collide with this with the origin. So that's what we assume. And the second thing is, in order to define the volume form capital omega, we just use that our phase space is just a cotangent bundle, so it has a natural symplectic 2 form, omega 0. And as such, it is scalar if you have the usual Euclidean Riemannian metric on this space. Yeah, so this makes it simpler to evaluate this volume of the Poincaré surfaces. So first of all, taking the default exterior power of the symplectic 2 form gives you a volume form on phase space. Then you take the symplectic Hamiltonian vector field, and in a product of this Hamiltonian vector field of H with this volume form, and then, you get this new M, which you want to integrate over the Poincaré surface HM. Okay, and now it turns out that in fact, by this codimension 2 remark, that means basically to integrate not the D's exterior power of symplectic 2 form, but the D minus first exterior power, with some numerical factor. And so that's easily done using the scalar structure. So you remember how the HMs were defined. The HMs projected to spheres Fm in configuration space. And so these spheres in configuration space have a natural Riemannian volume. And then you just integrate some power of E minus the potential over this surface to obtain this volume HM of with respect to this D minus 2 form that you have here. Yeah. Okay. So that's a very concrete question. Here you have the volume of a D minus 1 dimensional ball. Just a constant in front, only depending on dimensions. So you really have to perform this integral. But now you see that this E doesn't play much of a role. The V of Q may diverge like Q to the minus alpha. Now Q is 1 over M, so you have M to the alpha. Then you multiply this by this D minus 1/2. This is the exponent here. On the other hand, you have a D minus 1, which is the dimension of the sphere. And of course, this sphere is of radius M, so its volume scales like M to the D minus 1. Yeah. Okay, so that's a completely elementary estimate. And this is just a constant here. And now you see how this alpha smaller than 2 comes in. Namely, this first factor here becomes negative. And you also see how the D larger than 2 comes in. You don't want to have this factor be zero, because you want this to go to 0 as M goes to infinity. Yeah? And actually it does. Yeah? So for all energy levels, the singular set has measure 0, which is of course not a new result, but just serves to illustrate how you use this technique. Okay, now to see, the point is that if you just change the potential, let's say to be attracting and homogeneous of degree -2, then in fact this Liouville measure of the singular set for any energy is positive. And so in fact this estimate here for alpha smaller than 2 was best possible. Yeah? And the whole thing I would say about these kind of estimates is that in the way you want to have flow, want to have volume estimates on your phase space, which at the moment is the energy surface. But these volume estimates are sometimes not so easily done, because if you are, let's say, if you are considering, for example, the singular set, then in the neighborhood of a singularity, the speed or the size of the vector field might diverge. So we have a hard time to estimate in the flow direction the speed of how this flow lines are stretched. So, and this Poincaré section technique just takes care of this because it's perpendicular to this flow direction. So that's basically the idea. Okay, I come to part 2. In part 2, we want to show that for scattering of n particles in configuration space RD, collisions are of measure 0. Yeah. So just to set up notation, you have a joint configuration space. Every particle is an RD. We have n particles, so you are an R and D. And if the potential between the particle is singular, then you would like not usually exclude.
Andreas, sorry, there is a comment from Claudio. It's for alpha equal 2 and V non-homogeneous, right?
Could you repeat?
Can you go to the previous slide?
Yeah.
So is the For alpha equal 2 and V not homogeneous, is it known that the measure of the singular set is positive?
Yes. That's actually very simple because basically then you can go to radial coordinates, and then you have a centripetal barrier, so to say, an effective potential also diverging like a distance to the -2 with angular momentum square as a positive constant. And but just in this case, this barrier doesn't work because the potential is more negative than that. Huh?
Okay, thanks.
Can I also ask another question?
Yeah, sure.
So in your definition of the set trans, you require that you only miss finitely many of the Poincaré sections, right?
Yes.
What if you consider like a slightly bigger set, like a Borel-Cantelli kind of set, where you allow infinitely many hits, but not, all but finitely many? Do you still expect that set, once you intersect it with 1, to have volume 0?
No, not in general.
I see.
So
it's delicate.
I don't have a good short argument at the moment, but we thought about this, and I don't think so, no.
Thank you.
You're welcome. But maybe I'm in error. I have to, so I'm sorry, I don't have a good argument, but I don't think so. Okay, so that was our configuration space, and the hat points towards the fact that we excluded some fat diagonal where some particles have the same position, and also the phase space then, which is the cotangent bundle of this, has a hat, bears a hat, and then we have the usual kind of Hamiltonian, kinetic plus potential, kinetic being sum of all these non-relativistic kinetic energies, potential being sum of two particle potentials between particle I and j. So usual stuff. And then, okay, we have this singular set, like for every ODE, and then we have the collision set in this very special case, consisting of those initial conditions x, where at positive escape time t plus of x, the limiting position exists. And so that's what we would like to show, that this set is of measure 0. Okay, so this has been proven by Sari for dimension 3, the physical dimension of configuration space of a particle, and homogeneous potentials attracting with some inverse power of q to the minus alpha, and alpha being smaller than 10/7. Yeah? And for binary conditions, he showed that this is improbable for all alpha smaller than 2, which is again the natural boundary in this case.
Improbable, so, in which sense?
Okay. Also Lebesgue measure 0.
Okay.
I have this slang, which is somewhat loose talk, because I don't want always to specify the measure. But you see, in our result, it will be slightly different. So we fix the energy in this case. We go to this energy surface for this Hamiltonian, and then on this energy surface we have Liebel measure, and then we say that for all energies, this Liebel measure of the collision set intersected with this energy surface is 0, of course, if the dimension is at least 2, clearly, and the potential is admissible. Yeah, and we'll shortly say what admissible means. Just to compare this to the other result. So, for example, if the binary potentials are homogeneous of this form, q to the minus alpha for alpha smaller than 2, then this would be admissible, just as an example. Yeah? And the point is here that, of course, restricting the energy gives you a stronger result, because you may, in the end, integrate out dual measure to get Lebesgue measure. Yeah, or yeah, that's basically it.
Thanks.
Yeah. Was there a question or a remark? No. Okay, so I'll shortly say what admissible means, because this is somewhat ugly. I would like to hide it, but otherwise then there's no statement. So for V to be admissible, let's say at infinity, the potential should go to 0 or be bounded or whatever, that's not a point. Then the second total derivative of these potentials should go like distance to the minus alpha minus 2. Okay, this is also maybe somewhat acceptable, but then there come two alternative things. And basically these things mean that the forces between particles I and j are not too far from homogeneous forces in some way, at least bounded below by homogeneous forces of homogeneity minus alpha. Yeah? And this is somewhat ugly, yeah? Because you remember in the first result, I didn't argue with derivatives of the potential, just with the potential itself. So you might ask yourself, why do we have this complicated definition of admissibility, and can this be weakened? And I will very shortly argue that this cannot be weakened too much. There is something happening in n-particle scattering if you at least have the usual classical approach to this n-particle scattering. And the point is somewhat, and I don't really give the full arguments, that if we, for example, would, instead of having alpha here, having a factor of 2 here, alpha is strictly smaller than 2, and otherwise this estimate being fulfilled, then there would be a counter example in some sense. And I just want to say that there is some reason why we have this strange looking condition of admissibility here. But this is too subtle to discuss now, and not enough time for it. So, okay, I come to part 3, and in part 3, I want to give you some hints of how additional techniques could help in the question of non-collision singularities and non-existence of asymptotic velocity. And these are what I would like to call non-deterministic billiards. And I will give a motivation, which is an old motivation, but now I think with Richard and Jacques, we are on good way to really prove what I now give you as a motivation. Yeah. So think of something that I will call a non-deterministic billiard. Yeah. So you see particles, and every particle has a color, and this particle moves in configuration space. You see this motion in configuration space. The particle moves on straight lines with constant velocity until it meets other particles, like here or here, so with the red dots. Yeah, and then it may change its direction. Yeah, and total momentum, total energy of these particles that are colliding being preserved. Okay, so in a way, I would call this a non-deterministic billiard. I come to the more precise definition. And this is somewhat an ideal world. And what we would like to show is that for, let's say, Coulomb repulsion or for gravitational attraction or similar things, you could show that there are solutions of this n-body problem that in a limiting sense, for example, total energy going to infinity, mimic this ideal world of straight lines. Yeah? So you see here points where these particles come very near to each other. You have a quasi-collision, and here and here and so on. Yeah? So that's why these non-deterministic billiards were considered. Yeah? But they may be also of some interest in themselves. And they are also useful in situations where you have these non-collision singularities, for example. Okay, so what is a non-deterministic billiard? First, with energy conservation. So you have these n particles, and in the figure you see 4 colors here, so you have 4 particles, and they move with constant velocity, and at collision, there's, as I said, conservation of energy and total momentum of each cluster of particles being colliding. For example, here you have a cluster of a blue and a green particle, and the total momentum and total energy of this cluster then is conserved. Yeah? And then, okay, you could now look at how the direction of these particles is, and you prescribe so certain symbolic sequence. For example, here you have a collision between particles 1, 2, 3. So you write 1, 2, 3. You have 2, 4 collision between particle 2 and 4, and so on and so forth. Yeah, you wrote down all the collisions that are in this picture. And then we look at the variety of all the solutions of this non-deterministic dynamics. Non-deterministic because we don't prescribe outgoing directions. We just say that we have these conservation laws. Okay, we can slightly abstract this by saying that we have scattering by linear subspaces of some Euclidean vector space. Let's say d-dimensional Euclidean vector space with a scalar product. And then you have finitely many subspaces in this Euclidean vector space. Yeah? And the particle, the non-deterministic billiard, may collide with these subspaces. Yeah? To make this concept a bit more concrete, think of this E being RND for n particles being in configuration space D, and these subspaces being just enumerated by indices of 2 particles colliding, I and J, and a subspace Lij would be then the subspace of all positions on this n particle configuration space where Qi equals Qg, where these billiards have the same position. Yeah, so that would be an application to the former situation. Yeah, so what is a non-deterministic billiard in the sense? You move on straight line until you meet such a subspace. When you meet the subspace, then you're scattered, but the norm of your velocity, your speed, is conserved, and also the tangential momentum is being conserved. Yeah? So that's the abstraction of what we had before. And then you say, oh, you do the same. So you have a sequence of subspaces, which in the concrete application means a sequence of collisions of particles as before. So the subspaces L1 up to Lk. And then you look at the set of all realizations of billiard trajectories meeting these subspaces in the prescribed succession. Okay, so there's a first statement, namely only such itineraries of finite length k may be allowed, because if you have such a concrete non-deterministic billiard with a collection L of the subspaces, then there's a integer k of L, which tells you that every trajectory has at most k of L collisions. Yeah, so it's a finite number of collisions that is possible. Yeah? And you see, it's very important here that you have a collection of linear subspaces and not, for example, affine subspaces. Yeah, because let's say if you would have two affine lines in R2 that are parallel, then of course between these affine lines there is a non-deterministic billiard that goes back and forth infinitely many times. Yeah, yeah. So that's the first statement, and the second statement is that there's also some symplectic geometry in this dynamic. So prescribing this symbol sequence, so to say, and fixing the total energy of your non-deterministic billiard to be 1. You are in velocity space on a d-1 dimensional sphere. So in configuration space, you are in the cotangent bundle. And initial and final positions of this non-deterministic billiards are encoded by points on the same phase space. So this is a product telling you, okay, no, there's certain questions, namely, do these subspaces to have codimension 1 in the manifold or the tangent bundle? No, they don't need to have, and in fact, typically they don't have. Just think of n particles in RD. Yeah, so Qi equals Qj gives you then codimension d. Okay, I'm not sure. Okay, I think that could be the answer of this question. Okay, so basically what we prescribe is the data of this non-deterministic billiard before the collisions and after the collisions. So both of them are symplectic phase spaces with symplectic natural 2-form omega 0. So also the Cartesian product is a symplectic phase space, and then the prescribing these data means that you have a Lagrangian relation in this symplectic manifold.
Sorry, Andreas, did you receive the question in the chat? We didn't see the question. Okay, so I reread the question. Do these have codimension 1 in the manifold or in this tangent bundle? I'm not quite sure whether I just read this chat question now, and it was referring to the actual transparency. So my answer was that these subspaces L here don't have to have codimension 1 on this Euclidean vector space, and typically don't have.
I believe this was from some 30 minutes ago, and the question is already answered, I think.
Pardon? Okay.
I think you already answered that question some time ago.
Okay, it wasn't referring to another.
5:12 p.m.
I'm sorry. I'm sorry.
Okay, don't worry, don't worry.
Okay, so just to refer to the theorem, so this was with Jacques and Richard. The first of these statements could ring a bell with you. There has been this paper by Burago, Verleger, and Kononenko in the Annals of '98, showing that if you have deterministic billiards, then if they are just freely colliding and are strictly convex and so on, then you have only finitely many collisions. Yeah? And basically, the first result here is just an adaptation of the arguments. Yeah? Okay, so of course the point is that you have here something that you can understand in geometric terms, just a Lagrangian relation, Lagrangian submanifold in this symplectic manifold. Yeah? Although it's of course not just a Lagrangian relation in the sense of fixing initial conditions and then final conditions being related to them. It's non-deterministic. Okay, so I just considered non-deterministic billiards with energy conservation. Now I will consider them without energy conservation. And clearly the motivation not to fix the energy is to have to allow for infinitely many collisions. Yeah? So in order to have collisions, you would like to have 3 points at least that may collide, and call these points Q1 up to Qn, but here they have a twiddle, and this means that these are just the trajectories. They have constant velocities vi until they collide. At collision, you have time tk, and the number of collisions in the future is assumed to be infinite. Tk is ascending to maybe a finite or infinite time t. And now also technical point, these masses may depend on time. Basically, so what you want to model here is not particles, but clusters that are very tightly bound. Yeah, so tightly bound that looking upon them from very far, you're not able to resolve these particles. So therefore, if there's an exchange of particles at a collision between 2 clusters, then of course the masses will also change, but the sum of masses will be conserved. Yeah? Okay, that's a somewhat minor point of this model. The important point is that the momenta are constant during collision, but the energy, kinetic energy, is not assumed to be constant. Okay, so and this relaxation is actually very nice, because if you project configuration space to a subspace of configuration space, then if you started with some trajectories of this n-particle non-deterministic billiard motion, then after projection you have a motion of the same kind. And this makes it simpler to argue about properties of this motion. Okay, just let us look at 3 such non-deterministic particles. That's relevant for the 4-body problem in celestial mechanics, because then you have at least one cluster if you have non-collision singularities. So the statement is that if the moment of inertia, just this quadratic form in the positions qi, has a positive derivative at time 0, so the system is initially expanding and it has infinitely many collisions as assumed, then this moment of inertia grows exponentially in the number k of collisions that have happened, and the same for the kinetic energy. And then these 3 particles also align, and so on. Okay. Now, if you look at 4 particles, or non-deterministic billiards, none of these statements is true anymore. But if one can adapt this by giving this k another interpretation. So you have n particles. You have the set 1 to n, call this capital N. Consider this as a vertex set of a graph, and this collision graph for a certain time interval between t minus and t plus consists of the edges, pairs of vertices, so that at some time in this interval, sometime t, the positions of the two particles are the same. So, and this interval is said to close the chain if this collision graph is connected. And then Manuel Quaschner showed that under a similar condition for arbitrary number of particles, this moment of inertia grows exponentially in this number k of disjoint time intervals closing the chain, and the same statement holds for kinetic energy. It also grows exponentially. Yeah? And this gives you some model of very extreme events, so to say, also of deterministic motion. And that's my last part, part 4. So we are first looking now at non-collision singularity, so everything that is singular but not collisional, and C being the abbreviation. And okay, there have been results by Poincaré. If you have less than 4 particles, there's not such a thing. But for 4 particles, Mather McGehee showed that this can happen in 1 dimensions. And there have been results by Shia for 5 particles in 3-dimensional spatial dimensions that such things happen. And by Gerber, there was an outline of a proof that has been now done by Shu. 4 particles in dimension 2 also show this. Yeah? So this happens, these non-collision singularities exist, but Sari showed that for 4 particles and in dimension 3, they have vanishing Lebesgue measure. Yeah? If we are looking at celestial mechanics case. Yeah? And just to remind you what this 5-particle shear solution looked like, it was a messenger particle going forward and backward between 2 binaries and letting them go to infinity in finite time. Okay, so now call this potential between the particle long-ranged if for it the force is integrable. Force between particles is integrable at infinity, and call it moderated if the particles are very near to each other, the force obeys the law like the q to the minus alpha potential we had before. Okay, then, for example, these minus alpha homogeneous potentials have both properties, being long-ranged and moderated. And then Stefan Fleischer in his PhD thesis showed that for 4 particles in 2 dimensions at least, and long-range and moderate potential for any energy, this non-collision set at energy E has Liouville measure 0. Okay, last but not least, this asymptotic velocity, if it exists, is just the Cesàro limit of velocity, position divided by time, for time going to infinity. And this exists if the potentials are defined everywhere. In celestial mechanics, it does not exist for some initial conditions, as Sari and Shia showed. And for 4 particles and for a class of long-range moderate potentials, including these homogeneous ones, they also exist up to Liouville measure 0. Yeah? And this kind of result also uses this non-deterministic billiards without energy conservation as a backbone for applying this Poincaré section method. Yeah? And because my time is over, I just thank you for listening. That's it.
Thank you very much. Let's give you a round of virtual applause, and thank you for the talk. Are there questions or comments?
Very, very quick question from me, maybe. So, Andreas, you define that an infinite velocity that does not exist in your definition as for the asymptotic velocity. So, infinity is not allowed.
I'm sorry. I go back to this. So this is vector valued, yeah?
Okay. So, okay. Well, I mean, back to that.
I mean,
infinity is not something that you want.
I mean, there is a result, a very old result, in fact, that if this doesn't exist as a limit in RDN, then the norm diverges.
Okay.
Yeah. Yeah. Basically, this is von Zeipel, a version of von Zeipel theorem.
Thank you.
And given that we are on these slides, can I ask you what happens if n is greater than 4?
Yes, of course, this is a very difficult question. So, by the way, this result also includes that these the former result that the non-collision singularities also have valuable measure 0. Yeah. So this is maybe in some sense just a special case of this. Huh? But this means that n larger than 4 is really a complicated question. This is one of the questions that have been formulated as the questions for 21st century mathematics. So it's not very clear whether one can get results, but of course, we are thinking about these questions in a quite intense sense.
What is the main difference from going from 4 to higher than numbers of particles?
Yeah, for example, you see, because you have some energy reservoir, you have to have at least one non-trivial cluster of 2 particles. Yeah. So in fact, for this billiard model, if you go from n particles to n-1 clusters. Yeah. Because you have to have some energy reservoir if your velocity goes to infinity. This means that we just have this difference. I go back to this former slide between the case of n equals 3 here for the non-deterministic model without energy conservation and the n larger than 4 case. Yeah. So n larger than 5, larger or equal to 5 for the celestial mechanics case would mean n larger or equal to 4 for this particles. Yeah? And therefore, the whole dynamics is much more subtle because it's about closing a graph and so on. Yeah.
Thanks.
You're welcome.
Are there other comments or questions?
May I ask a question? And so, what is the situation instead for bodies, but dimension 2? So now we know that there are non-collision singularities even for the Newton potential. What's the measure of this set known?
Yeah, I mean, I didn't succeed in showing that you have finite measure in 2 dimensions. I'm still confident that this can be done. But
I mean, 0 measure.
Yeah, I'm sorry. Now I just.
Well, that's the fun of the live.
Okay, so yeah, so I'm back. So actually, it is not clear whether we have a 0 measure for 2 dimensions or not. Huh?
Okay.
State of the art.
Mhm. Thanks.
You're welcome.
So the landscape is really varied.
Yeah, I mean, at least it's fun.
Oh, yeah.
Okay.
Are there other questions or comments? If not, thank you again for the very nice talk. And I'm giving you another round of virtual applause. We can even use the emoticons here to say, yes, clap.